Greetings. In this one I will prove that if we have a group with exactly 3 elements, order of 3, then it must be abelian. So G is such that its magnitude is 3, its number of elements is 3, is abelian. We suppose that. Well, we will try to disprove it, and by contradiction we will see that indeed it is true that if a group has exactly 3 elements, it must be abelian. So in general terms, if a group has 3 elements, it still has to have the usual group properties. So it must have an identity element, and it has to have some 2 more elements. But we have to be careful because these 3 elements must be distinct. If we are talking about the group of 3 elements, all 3 elements, the reason it has 3 elements because these 3 elements are not repeated. So x cannot equal e and y cannot equal e. So the only way we can have an inverse for y and x is them being inverses to each other. X must be the inverse of y and y has to be the inverse of x. And we also need, well, abelian will mean that xy equals yx. That must be fulfilled. That means abelian, that it's commutative. The order of operations doesn't matter. So in such context, this is what we are trying to prove. And so I will use contradiction for this. So we've already established we have identity element E and then some 2 more elements x and y. And by direct logic, it must be so that x doesn't equal E and y doesn't equal E because we have three distinct elements. And also, x times E must be x because the identity commutes. X times E equals E times x. And the identity element multiplying some general any element of the group from either side will result in that element again. So identity element doesn't change it. So if x is different from y, then ex must be equal to xe. Nothing, and that must be equal to x. And the same for y. E times y equals y times e. So that's this idea, by the way. And also, well, this is general. This is not even needed to be abelian. So, well, for every group we have something called the central elements that commute with all other elements. They're basically like kind of the abelian core of a group, even if the group as a whole isn't abelian, isn't commutative. Not all elements commute. Then at least some will, sometimes, for example, and we can find those. And well, this same thing, by the way, ey should equal to ye should equal to y. Alright, so these are general things for the identity. And let's now use the contradiction principle to prove that a group of exactly 3 elements must be abelian. So let's say that it is such that xy equals x. And well, this doesn't make sense because xy must equal e because we have only one possibility of an inverse for x, and that is y. So the result should be e. But let's see that it doesn't end up so. And there will be a contradiction because neither x and y, as had been stated before, can equal to e, which is where we'll actually get. So if I multiply both sides by inverse of x from the left side, we have this. And then the inverse with original element will create identity element, doesn't change anything. So that's just y times the identity equals the identity element. So that says that y equals e, but that cannot be true because y and e must be distinct. There's 3 elements and e is already taken up one place and y is another. It's general. And then now another contradiction. So we've already contradicted this. Another contradiction will be based on this equation. xy equals y. So what I want to do is multiply on both sides from the right by y inverse. And that will yield in the end this. X equals e. So this tells us that x is the identity element. So that would mean that x equals y equals e, and that would at the end of the day mean that x and y and e reduce to just e, that everything is e. So that's a contradiction. So if I said that xy doesn't equal yx, it won't work out. And so it must be so that xy equals yx equals e. So x and y are inverses of each other and they commute. And so if a group has 3 elements exactly, it must be abelian.